Okay, cool. So you guys seriously have no questions from me? Nothing. It's all going great. Someday I'll actually get some of it from some of you guys. Okay, all right. So we had just started looking at section 4.1. Oh, yeah, dude. All right, sorry. Get excited about small things. Why? We had got to the point, I think, where we talked about critical points. Just to remind you guys what critical points, critical numbers, really. So it's not really a point. Critical numbers. These were the possible locations of local maxes and mins. So what the shit is a local max or min? Possible. And why is it just possible locations? And one word is kind of say this quickly. This idea of max or min is extrema. That takes care of both. So you might see them say something to find the relative extrema. That's another way to say local max or min. I like it. Extremely big, extremely small. I like it. Possibly. Okay. So the critical numbers are where these things might happen. And we've actually known about this connection for a while. When we started drawing the f prime over some given f of x. Remember that? Trying to trace what the slope would look like before we even knew how to take derivatives? You were graphing them before you knew what they were. Okay, I like it. And of course, what did we do if I gave you like the buck graph and I said graph f prime, what would you graph first? If I said here's f, graph f prime, what would you graph first? Anchor points, which are related to where its slope is 0. I love it. And how do I tell really quickly where the slope is 0? It's going to be where the thing is locally biggest or locally smallest. Yes? And local what? There. Right? Could it get bigger? Maybe it gets way bigger than that. So that's not the extreme. This is an extreme. This is a local maximum. I like it. Like I climbed this hill and somebody's like, you didn't really climb shit, bro. I'm like, I climbed, shut up. It's not the highest point. It's still kind of high. Okay, I like it. So one place where you find critical numbers, what are the places you can find them where f prime of x equals 0? That's the one we've known forever. And the other one, another place where this could be true, this is kind of a weird way to think. How in the world could I make a maximum where the derivative doesn't exist? Because that's the other place where f prime is undefined. So what would that relate to visually? Where is something not differentiable? What is one of the most basic places something's not differentiable besides where it's discontinuous? How do you get something that's not differentiable? When it goes to infinity. Or kink. Corner, some kind of sharp edge. Is that a maximum right there? Please say yes, because it is. It's the biggest thing there. But is the slope 0 there? What's true about the slope there? It is undefined. So where could a max or a min happen? Where the slope is 0, because that's related to what we were doing before, or where it's undefined, because it could relate to that. Now, why do I say possible? Where could it happen? These aren't definite things. It doesn't definitely have a max or min there. Because, like you just said, here's somewhere else that the slope is. Right in here. Right where it goes to infinite slope. Is that a max or min? No. Here. Slope is 0. It keeps going. That's not a max or a min. It's just a little resting point, right? So these would still be critical points. And then I have to test them to see if they're maxes or mins. Let me see what else can go wrong on them. All right. So then we got to develop tests once we find critical numbers. Oh, sweetheart. Okay. There. So let's try a concrete example. It's always nice. Concrete, please to God, Jeff. Concrete example. Let's try one that's not too terrible yet. Let's make it, screw it, it's fine, Jeff. Are you able to tell me what kind of function that is? I always love this question. You're like, what do you want from me, Jeff? You could say differentiable, and I'd be like, that is what function it is, sure. It's a polynomial function, right? It's just not multiplied out, but it's a polynomial function. It's going to have beautiful derivatives. It's not going to be undefined anywhere. So the critical points are only going to be where it's 0, where the derivative is 0. So take a real quick derivative of that. Oh yeah, might as well. Why not? All right, let's take a look here. Let's see who's working. You're sort of working. You're sort of working the same amount. Okay. So what is the kind of like the main rule I'm using on this guy? The main one. I see a few people. Yeah, product rule. I love people like product rule. And involved in that is going to be a little bit of chain rule. I don't have to know that ahead of time. I just got something times something. So let's see. This guy, the 4 comes down. Cubed. Leave this guy alone. The inside's linear in x with a slope of 1. So there's not going to be any chain rule piece to it. There's times 1. Ooh, right? Plus, leave this dude alone. And how you take the derivative of this last guy. What happens here for this guy's derivative?
Take the derivative of the inside function.
Well, first thing you do is take. Are you guys all right? Did all of you make it back? Did the entirety of you make it back from break? So it's something to the 3rd power, the 3 comes down in front of the thing, to the 2nd power times, like T said, derivative of the inside. All right, and then this is where some of us lose it a little bit, but this should be the easy step. You factor this bad boy, right? Why can't I just go ahead and set this equal to 0? Because this is a sum of things. Setting it equal to 0, it's not in the right form yet to see what's going on. I got to get all the factors out. So what can come out? I know I got 3 times 2. Who cares? Because I can take a 2 out. How many x plus 1s? 3. And how many 2x minus 1s? 2. This is where everybody should be able to sink their teeth in this thing. You might just be too easy. People don't like to answer when it's too easy. So then what do I have left here? I've got 2. These are gone. I got 1 of these. So I got 4x minus 2. Is that cool? 2 times 2x minus 1. Over here I've got an x plus 1 left and a 3. All this stuff left. So I got plus 3x plus 3. So I end up with neato. I like it. Yes?
Why did you multiply 2 times this one?
Oh, for this?
Yes.
Okay, so if I take a 2 out, I have a 2 left here. I took all of these out. I have 1 of these left. 2 times this. Yeah, I like it. You can show yourself more steps. I'm just going to get through it quick. Okay. Is everybody cool with that? I mean, that's... You know I could be very blunt. And if you're having a lot of trouble with that, that's bad. It's a very bad situation. It should not be true. Can anybody tell me what the critical numbers are for this then? Critical numbers. Negative 1. 1/2. Negative 1/7. Just, I got it all factored so I can set it equal to 0 now. I like it. Okay, I like it. Now, I'm going to go further with this. Section 4.1 just asks you to find the critical numbers. Section 4.3 then asks you to test those critical numbers to see if they're maxes or mins or just little resting places. Are you guys kind of with me? But I'm going to go ahead and do that step. What the shit? Why not? We got critical numbers here. Why don't we just go ahead and finish that bad boy out? So this should look familiar. I think we did something like this earlier. Or I mentioned that we're going to do this. So if I put a little number line down, and I've got negative 1, negative 1/7, and 1/2. Beautiful scale. This is just, here's where you as a student have got to start asking more questions about, when you give me a graph of something, and you do this shit and that's your answer, that is shit. That's shit. But this is not a graphical answer to a question. This is just the middle. This is a little visual anchor thing I want to work with. So the scale sucks. Who gives a shit? But as a student, I understand how it can be frustrating. Sometimes scale is really important. It's not. That's part of what you got to figure out. This is just a quick little middleman. What am I going to do with this weird thing? Well, at negative 1, the slope is 0. Is that cool? In fact, at all of these, it's 0. So put little z's up there. What would I put up there if it was undefined? I'd probably put a little u up there. Stay with me now. This is kind of cool. Could just be me that thinks that, but I'm okay with that. Now, do you guys remember? All right. This is not absolutely necessary to know, but it really makes this a lot quicker, and you're going to be doing this a decent enough amount of times. Multiplicity. Have I talked about multiplicity yet? It's huge. And again, it's not just a movie with Michael Keaton. You should see it if you never did. It's kind of fun. This factor is parabolic. Is that cool? 2x minus 1 squared. It's parabolic. Meaning, at its 0, it would touch it in turn. It won't change sign at its 0. Where's the only place this slope could change sign? Where are the only places where the slope could change sign? Around the zeros. What's the only way that if I have a positive slope, it could become negative? If it's a continuous function like this is, what's the only way it can become negative? It's got to first become 0, and then it can become negative. And how's it going to become positive? It's got to become 0, and then it can become positive. So I call these my doors. Right? Get away from me. Okay. So, here's where multiplicity and the idea of it can only change signs around a 0 meld together and make this beautiful. What's the easiest number to plug in any of these things? 0. Let's plug 0 in. Let's put it in the right place, Jeff. Here's 0. What's the slope at 0? Is it positive or negative? I don't give a shit what the number is. You guys with me? I want to know if it's going up or if it's going down. Positive or negative. So 0, positive, positive, positive. You guys with me? So positive, 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 positive. Okay. So in here, this whole region is going to be positive. It's going to be going up in that whole region. Now I could continue. I could put a 3 in there. I could put a negative 1/2 in there. I could put a negative 18 billion in there and see what the sign is and do the same thing if you don't like the shortcut I'm about to say. What's the only element here that's got an even multiplicity? Where's the only place that a root shows up an even number of times? Which root? 1/2, right? Showed up twice. It's going to act like a parable. I like it. A parabola. It's going to turn at, what did I just say, 1/2. So here, it's not going to change sign. Everywhere else, it's going to change sign. I'm done. Thank God. I only had to put one stupid number in, and I put the easiest stupid number in. Of course I did. Now, like I said, you could put in there -4, and then you get negative times positive times negative. Negative times positive, negative is positive. You can do that for every little region that you created to check. But multiplicity makes that damn thing so quick. So watch this. This is kind of cool. This is remarkably awesome. I can do a real quick rough sketch of what this thing looks like just on what we've done. Because what's it doing here? What's it doing all the way up to -1? What's that function doing? What is this a graph of? A plot of? The idea of what?
Like slope.
Slope. That's the idea of slope. So what's the function doing back here? It's going... It's got what kind of slope? Positive. So it's going up. What's it doing here, right there? What's it doing there? What's it doing at -1?
0.
0 slope, so what's it doing? Flat. It's flat there. Right? Flat. Then it's going down. Then it's flat. Then it's going up. Then it's flat. But then it's going up again. Stupid little thing. That is nowhere near a good enough sketch to give me as the final answer if the problem said graph this, right? But this is a really, I mean, look at this decent little thing that I just kind of plotted out. Now, the grosser the function, this is a nice function. The weirder the function gets, the weirder it's going to try to be to piece this together. But you normally can get something that's pretty close to the overall shape of the damn thing. Can you see where there's a maximum? Where? -1. There's a maximum. There's a local max. Is it the maximum of the whole function? No, this goes up forever. But this is a local max. So can somebody help me? What's the local max? Local max is -1 what? How do I get the what? How do I get any output for any function if I know the input? I probably plug it in. Isn't that crazy? So how did I get these? What did I use to get these? F prime. Why? Because I needed to know where it was going. Was it going up or down? Now I need to know where it is, not where it's going. So I have to use F. Now, of course, when you plug a -1 into F, you get very little work needed. What do you get when you plug a -1 into F? 0. Okay. And now this guy is going to be where there's a what? A local minimum. So a -1/7 become a real number. There you go, Jeff. Something or other than that's where you're going to have to do a little work. I don't know what this shit. 6/7 to the 4th power. That sounds great already. Let's see. 9/7 to the 3rd power. Oh, scheisse. It's gross. I don't know. You guys get calculators, right? What's happening right here? Is that a max or a min? No. It's just a little resting point. So my critical numbers, there are 3 of them, but only 2 of them came out to be extrema. I like it. And you just plug in the calculator and get whatever the shit that is. Okay, I like it. Maybe. All right, let me see. I don't know if this will be... Let's just do this real quick. Because if you're not doing this for yourself... Some of you guys do this too much, and some of you guys never do this. It's kind of crazy. You need a little balance. What am I talking about? Plot the damn thing in the graph and just check what the hell you did. Let's take a look here. So who's who? This one's this one. All right. All right. All right, let's take a look. So here's the function, right? Woohoo! Dude. Yeah, looks right. Yep. So now if I zoom 6 this bad boy, it's a little bit far out, right? In fact, I can kind of see my scale. I only need to go down like -2 and up to 1 to really capture this whole thing. Are you guys with me? So let's kind of do that. Let's make this from -2 to 1. Funkadelic. See how it goes up? Now it's a lot flatter here than on my little rough sketch. Why is it so flat there, do you think? Because it's a 4th power there, right? So the higher the powers on this, the flatter it gets. In fact, if you did x to the 100th power, it would look like a funky U, like this. Really flat at the base. And then it goes down. It didn't go down near as deep as I wrote up here, but again, it's a rough sketch. And then it went back up, and then it rested, and then it kept going up. Here, for those of you who didn't survive spring break. Okay. Are you guys kind of with me? So, you have to balance this correctly, because I love it when somebody gives me completely wrong work, but then the graph is perfect. No. I'm going to say this a few times. If your calculus comes out with mistakes, and you can't see what the mistake is, you graph it based on your work. You'll see here when we get to the more the beefy graphing sections 4, 3, 4, 5. You're going to do a lot of work, you're going to get all this stuff, and then you're going to graph it according to what your work says. So if your work says it's supposed to go down, you better make it go down, even if on the calculator it's going up. You're going to lose less points if your work matches with your graph. Even if you made mistakes, if your graph is beautiful, I'm going to take a lot of points off, because I'm like, you never showed me that you understand how to translate from what you did to what it looks like. I got to see that. All right. So again, 4.1 is going to be focused on the critical numbers. This, what we just did, this is going to be a big part of 4.3. This is remarkably enough. What did I use to construct this again? What did I use to construct this? How did we get the plus and the negative? What did I look at? Of what? Of the f prime. So this is called the first derivative test. We'll learn later that there is a second derivative test that sometimes is quicker than this, and sometimes it sucks. So it's there as an option. We'll learn it later. Now, here's the other idea in section 4.1 besides relative extrema, besides local mins and local maxes. So if I just want to know the absolute extrema, which means the absolute biggest the function gets and the absolute smallest the function gets, those could happen at the critical numbers. Or they can happen at the endpoints if I have a restricted domain. So for example, if I have this picture here, where up there would the absolute max be? Yeah, way over here. That's the absolute max. At the endpoint, right? And where's the absolute min? I love you guys. No, just do this. It's here. And where would that be? What is special about this point, this number? That would be a critical number, right? So it could either happen at the critical number or it could happen at the endpoints. How are we feeling? Absolute extrema. Did you guys enjoy this? I mean, this wasn't that hard, but it's still kind of a little bit. Absolute extrema is so beautiful. All you have to do is find the critical numbers, plug them in, plug in the endpoints, and see who wins. I don't have to be so precise, because all I give a shit about is what's the biggest, what's the smallest, right? So here's let's do an example. Let's see. Blah, 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 blah. Blah, blah, blah. There we go. This one is a little more interesting. That looks yummy. Yeah, why not? And they give us a range. Yeah, okay. Let's see what kind of problem they have created. So the question would be, find the absolute extreme. Let me see exactly how they word it. Well, it's the absolute max and absolute min, because they enjoy wasting ink. But you could just say absolute extrema. Considering the list of things, which one of these is the easiest one to kind of pin down? Well, I know the freaking endpoints are 0.2 and 4. So I know eventually I'm going to plug those bad boys in to see how big and small they are. But what do I need to also check? I need to find what? What else do I need to find? Yeah, zeros of. Not just zeros, be careful. You want to find the critical numbers, which is where the what is what. What's critical numbers? How do you find critical numbers?
Where the slope is 0.
Slope is 0 or undefined. I love it. That's the danger of doing an easy polynomial problem first. You forget that second part. It's 0 slope or undefined slope. That's the collection of all critical numbers. So real quick, do that. Find the critical numbers for that function. Find the list of critical numbers. You should be getting 3 critical numbers. Let's see if that's true. I'm not going to check all of them though and see why. See if anybody knows why. What is the derivative of this? Okay, because that's x to the negative 1. Negative comes down, it becomes negative 2. So I get 1 minus 1 over x squared. Where's that undefined? There, I got a critical number. Critical numbers so far are 0. When is this equal to 0? Can anybody do that without doing any work? Although you should have to do the work too if it made you. 1 minus what is 0? 1 minus 1 is 0. So when is this 1? When x is 1 or negative 1. Okay, so I got all my critical numbers. You could multiply by x squared minus 1, factor x plus 1, x minus 1, you could do blah, blah, blah. Or you could look at the equation and see what it's actually trying to say. All right? The more you know, the less you should have to do. Why am I not going to check all of those? Which one of those will I actually check? Is there some kind of restriction on this problem? Yeah, I've got to be here. What's not in there? 0's not in there. And negative 1. All right, sweet. So what do I have to check? Now here's what it is. I got the endpoints. They got to give me those. Get the critical numbers. I got to find them. But, derivative set equal to 0 should be simple. And now all I do is where am I going to plug 1 and 0.2 and 4? Where am I going to plug them? Into f. I love it. This is huge. We're going to bring f double prime in eventually, and f prime, f double prime all tell you different things. So you have to know really where you're plugging what at the moment. You got to really be aware of that. And that's why some of you guys that don't even write for yourself, you just put down here equals 1. I'm like, what? No, f prime. Tell yourself what you're doing so you don't lose track of what's what, especially now. So all I got to do now is put in f prime of 0.2, f prime of 4. Get out of there, f prime, Jeff. F of 0.2, f of 4, and f of 1. Plug them into the function so I can see Where is it the biggest output? Where is it the smallest output? That's awesome. I don't have to do a number line. I just plug them in to see who wins. This award and that award, right? I don't know. What's that for 0.2? 5.2? You guys going to just trust me on that? I don't know. You sounded pretty clear on that, Jeff. And then 4 is 4.25. That's easy enough. And then 1 is 2. What's the absolute max value? What's the absolute max value? So it could be over here now. I'll put everybody to sleep. What's the absolute max value?
0.2.
No. 5.2 is the absolute max value. And what's the absolute min value? 2. If I said, where does the absolute max value happen? 0.2. Where does the min happen? 1. So something in pre-calculus they should have made a big deal about is when I say, where does something happen on a function, that's x. When I say, what is happening there, that's y. Okay, that's awesome. Look at that little tiny problem. That kicks so much ass. So when they ask you for absolute extrema, the work is relatively simple. It's very straightforward. Local extrema is a little more ambiguous. Okay. Let's see. Oh yeah, so we'll do that. Okay, let me switch these out. All right. So that's 4.1. The idea of critical numbers, the idea of local max and min, and the idea of absolute max and min. 4.2 is an interesting little section. It deals with a theorem that once you see what it says, it's like, duh. But it's a basic building block for other theorems. You see it referenced in a ton of other theorems. That's why it deserves its own little section. And it's called the mean value theorem. Now let's start with, I think they start with, yeah. So we're going to start with Rolle's theorem. We'll kind of build up to mean value theorem. Okay, so here's the idea. If I have a continuous function and differentiable on a, b. All right, so this function is continuous, differentiable on a, b, so it's not allowed to teleport and all that kind of weird shit. And f of a equals f of b. So for example, here's f of a. It's the same thing as f of b. So what could the function look like in between those? The most basic thing it can look like would just be straight line, right? But let's kind of, so here's the idea. Here's the, as the crow flies kind of way to get there, right? That slope is what? 0. They're the same height. Slope's got to be 0, right? If I did not go straight from A to B, then I could do something like maybe I could do this. Let me do different colors here. I could do wee-haw, or I could do woohoo, or I could do right? Any of those options, they're all continuous, they're all differentiable on A, B. And they all end up with the beginning is the same as the end value. What's true about every single one of them is at least one place they have to have a slope equal to this slope, namely 0. That only makes sense. If I turn away and I'm supposed to end up over here, I've eventually got to turn back. And what's the only way I can kind of get back down to it is if I go through 0, like I said earlier. You guys, so Rolle's theorem is especially kind of duh once you see what it says. If I start in the same value that I end up at, somewhere in the middle the slope's got to be 0. So obviously if I just go straight, the slope is 0 on the whole damn thing. But if I don't go straight, if I go up, I eventually got to go back down at least once. So there's got to be a 0 slope. If I go down and up and down and up several times, then there's a bunch of 0 slopes. And this theorem just says at least one. How's everybody doing so far? You guys all right? I can't read you, and I feel like you all get together and like, everybody has worked on their poker face? Yes. We've all done it. Now watch, this is kind of awesome. Let me make sure. Is everybody really cool with this? I mean, this isn't huge. See why it's got to be continuous, though? If it didn't have to be continuous, I could just go, all right, I'm going to start over here. I'm just going to teleport down there. So then this wouldn't mean shit if it wasn't continuous. But most functions we deal with are continuous on their domain. So this theorem actually is pretty robust. Now, what's mean value theorem? Okay. Now watch this. It's kind of cool. All right, let me see if you guys... If everybody looks at this and just does this, there's mean value theorem. What the hell am I talking about? Mean value theorem takes Rolle's theorem. It says, good job, Rolle's. Really, that's really great. But what if I have still a function continuous and differentiable, but now the outputs are different? See what I mean? So I've just taken that and turned it. So now it's here. What's the slope of this line that I just drew? I love you guys. Go back to algebra. What's the slope of that line? Don't tell me 7 or something that's like, holy shit. No. What's the slope of that line? How do I get it? Yes. F of B minus F of A over B minus A. I love it. Right? So that is now the more general way of looking at slope 0. Mean value theorem says Rolle's theorem. That's great, but it shouldn't matter what the slope is. If the slope from A to B is this, then no matter how I connect these, if I start going higher, faster, eventually I'm going to have to turn to come back, and there's going to be a parallel place. There's going to have to be at least one place between A and B. There's going to have to exist. You're going to love this. You ready? There exists. That backward Z means there exists. I need one more either. Just there. There exists at least one value C in A to B. There exists at least one value C. So that would be like right here for this picture, right? Where the slope of the straight line is equal to the derivative at that point. So really I'm just saying the slope equals the slope. That's crazy. So there's got to be at least one. So what if I would have went this way? Or what I went, okay, but eventually I'm going to have to turn around at least once, and they're in parallel, and they're in parallel again, right? There's got to be at least one place where the function itself is parallel to the straight as a crow flies. Yes, 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 maybe, maybe. So that's exactly this, just turned. That's all. So instead of a horizontal line having a slope of 0, it could be any line with any slope. There's got to be at least one place where the slope equals that. So how do I write that officially? So that means the slope at C has to equal the straight line slope that you guys just told me. So again, that's all theory. We'll do a concrete example. Sorry. I do enjoy sometimes reading my reviews, and I always remember this one kid that said, he's literally there just to explain the concepts. Like that was a dig. And I'm like, that's literally my job. So, thank you, I guess. But I do show examples. I don't know if you've noticed that. I show examples. So let's do an example here. Yes?
So, the mean value theorem is kind of like an extension of Rolle's, but not Rolle's theorem.
Rolle's theorem is like it's actually the one that was come up with first. But if you look at it like this, Rolle's theorem is a specific instance of mean value theorem where these two are equal. If these two are equal, the slope is 0. Then you get Rolle's theorem. So mean value theorem is more general. I like it. But in a lot of history and math, we got the specific thing and we went, wait a minute, can I generalize this? Yes. Oh, neat. Okay. So let me take one out of the book. Blah, 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 blah. Let's do a mean value theorem. There you go. Sure, we'll do that. What's it say? 2x squared minus 3x plus 1. All right, put a little marker. What do you got? 0 to 2. So the instructions in the homework and on the test are going to be verify that the requirements are met and then use the mean value theorem to find all values of C. So what are the requirements? Anybody remember what F has to be true about F? Continuous and differentiable. I like it. And to be really, really honest, it has to be continuous on the closed interval and differentiable on the open interval, which is a small point, but still, it's there. So is that continuous? Oh, shit, yeah. Is it differentiable? It's a freaking polynomial. So that's awesome, right? So how do I do this? Well, the idea, how do I find C? Well, I know that f prime of C has to equal f of b minus f of a over b minus a. So then I just start working with that. How do I get, this side is easy, this side is easy, right? No? Yes. So I get, for this side, f of 2 minus f of 0 over 2 minus 0, that's that side. How do I start to work on the other side? What do I need to create?
Graph.
Don't need the graph. I know there's a lot of graphs to discuss this idea, but now I've got the idea. I don't need the graph necessarily. Not a bad idea, but you don't really need it. I need what? What's f prime? So what's f prime of C? And when I did this as a student, I never used the letter C, but I'm going to try to do that because I think the book doesn't. So what's f prime of C? What's f prime of C? 4c minus 3, thank you. Solve that. Go ahead, do it. Finish that up. Solve it. The only thing you don't know is C, and that's what I want to know. What value of C actually has this thing happen? There has to be a place because it met the requirements. Comes out really nice. Bless you.
Thank you.
Oh, I can do that. Let's do that. what are you guys getting over here? F of 2 was 8 minus 6 plus 1, 3, I think. 3 minus 1 is 2 over 2 is 1. Cool? I need to stop asking that. Let's see. You guys will never let me know. And so C is 1. Cut to the chase. Yeah. And one big red flag that you've made a mistake, which didn't happen here, thank God, is if your C value is not in here. That's obviously. If you got 3 here, it is, I'm wrong. It's not even in the valid range. Okay, I like it. And I know it sucks. There's so many places you can make a simple mistake, but thank God you got a teacher that gives you partial credit. Okay. So that idea, it might have sounded really weird when we first talked about it, but the idea itself and then the actual just nuts and bolts of how to apply it are really nice. Now, there are some very interesting problems in this section. Is this the one? No. I guess it's coming up later. Darn it. There was a problem about a monk climbing a mountain. Maybe that's coming later.
One of those a while ago.
Was that a while back?
That month.
Yes. Oh, that was back there. You could do it here. Okay. Okay. So, 401 was critical numbers, local max and min, absolute max and min. 4.2 is the mean value theorem. 4.2 is kind of like a little short thing they just had to throw in there because a lot of the theorems you're going to see are going to involve mean value theorem to prove them. Section 4.3, and I might as well just put up here the fact that it's related to 4.5 also, are the sections that, unfortunately, I think a lot of you guys are just not going to like much at all. But 4.5 especially is going to bring back horizontal asymptotes, vertical asymptotes, a lot of stuff you should know from pre-calculus. 4.3